is Mehreen from ML Lab. So please introduce yourself and your company.
So my name is David Redmond. I'm the VP for machine learning, AI, and silicon development for Equal One Labs. Equal One is a quantum computing company where we're going to where we're developing a full quantum computer solution with applications for machine learning, deep learning, things like that. The company is a startup. It's a spin out from UCD. It's been around since 2017, I think. We've roughly about 12 employees now. And we've developed two versions of quantum computing prototypes. So we're doing experiments, gathering data, and preparing for another version of the silicon, which will have different quantum structures on it, as well as some other I guess, proprietary circuitry that we will use for to control the quantum computer, basically, yeah.
That's very interesting. And there's another thing that we are very interested in knowing, that how did you get into a career in machine learning?
So I have a lot, I guess, for about 20 years, I've been working on silicon products for a variety of multinationals. Most of the products have gone into consumer space. So this will be chips for handsets, for cell phones, 2G, 3G, also products for Ethernet, gigabit Ethernet, mostly in the RF and high-speed gigabit Ethernet for laptops, for switches, some for commercial use, but for the most part, it's been consumer grade electronics. So I kind of wanted a little bit of a break from that, and I started doing a master's in UCD in data analytics, in mathematics and data analytics, because back in 2014, well, machine learning was was being talked about, but didn't really get going. So that was my break in my career from electronics to machine learning. After that, that was a part-time master's, so I was working and doing that master's at the same time. Then when I worked with analog devices, and I was able to start using some of the knowledge and skills that I had picked up in that master's, particularly for things like looking at IoT type solutions. So within analog devices, we had a product that was trying to predict the life or the time to failure of critical equipment. And to do that, we needed to gather vibration data, and we needed to build reasonably sophisticated models. Not deep learning models, so to speak, because the data wasn't suitable for that. More predictive models. So this was very much a what people call now shallow learning. So you gather all the data you can, you build up some models based on predefined existing conditions, and then you use that to apply that. You kind of map those models across to your IoT data, and you predict. That was very successful, actually, but so I still, but bigger emphasis was on the electronics rather than the machine learning. So I wanted a bit of a break, so that's why I came to Equal One. Equal One really wanted to combine machine learning in the hardware and with the physics, with the quantum physics. So that was very interesting. There's a strong mathematical bent on that. There was a strong innovation opportunity to innovate. And it's not just in the circuitry, it's also in machine learning aspect of it and applications. And operating at 3 degrees Kelvin, it opens up lots of possibilities for semiconductor design. So it has a lot going for it. So it's quite interesting for me to do that.
Yeah, I mean, it's quite interesting for us just to hear about it, and you've been doing it, so it's really amazing. So my next question is, do you think we can achieve general artificial intelligence? If so, when? And if not, then when?
Um, so, okay, very, that's a very broad question. Um, I, I, I don't see how it's going to work quite so easy. One of the challenges we still face today with all this, all the talk is how to adapt an algorithm quickly from being an expert in one area, like if it's reinforcement learning, it might be an expert at chess. But how do you take that solution and say, well, okay, instead of playing chess, I want you to play Go, or I want you to play something else, backgammon. So you have to retrain and redo all those things. So that actually is a serious. So we've built machine learning solutions to solve very specific problems, but they're not very portable to go and jump from one to another. Unlike a human being. A human being is very adaptable. You know, when you learn to run or learn to walk, you quickly learn that, and you quickly transfer those skills, even though they're quite different, to cycling. So we're far more adaptable with our learning knowledge than we find typical machine learning skills. Like now, if you look at the more the kind of celebrity models that are out there today, like GPT-3, that's very good at doing a specific task, but it's not transferable. So until we find ways to make it more transferable and more like a human, I think we have a bit of work to do. And that to me is quite interesting because that exposes a weakness in what we're doing today with the way we're training our models. So we're training our models to be quite rigid, quite fixed. They have to be, really, because they're trying to pick out fine features and fine details and recognize those fine details. But how do you retrain quickly a very deep, a large amount of data or a very deep corpus or big corpus of information without burning, another Amazon rainforest, which is basically what GPT-3 is doing.
So human
So
race,
we're missing.
yeah, sorry, I was just saying, so human race is not in danger from robots,
No,
unlike what is being said in movies.
no. In all cases, they are aids to humans. In absolutely all cases, they help us make better judgments. That's what we should be using them for. But they don't replace humans.
Right. So, from your experience, what proportion of developed model were utilized or put in production by your organization?
What proportion of, maybe just elaborate on that a bit when you say proportion of models? What do you mean by that?
Like you guys have been doing some work, right? And then you take the work into production, into field, into actual development side, like where you are using it into real life to solve the real life problems, and then there would be some in-house projects. So I'm just interested in knowing what proportion of these model is in production, and what is sort of still developing and you think is not ready to be applied in the real life.
Yeah, so we don't have a model essentially that's out in production at the moment. We're a little bit early in that stage. Um, Now we've ambitions to do that very soon, but we don't have one that's out in production. We have demonstrators. So we'd
Okay.
have something like one of our demonstrators we're going to release before the end of the year is a unit. A unit it's been around for maybe 5-6 years. It's proven to be very useful for specific problems. And I come back to the specific problems. And what we're doing is adapting that model to exploit the characteristics of quantum noise and to improve on the training. And so that's kind of what we're doing right now. And we have a kind of a collaboration with a number of people to do that. So we will release that. We will release basically the model as a template for people to play with.
Mhm.
And then they can, as part of that, there's an API call to our quantum computer to take the quantum noise that actually improves the learning in that model. Now, these are demonstrators, so they're not really in production. Um, One of the other ones we did look at was using faster RCNN or a mask RCNN model to help with chest X-ray detection for uh, COVID X-rays.
Mhm.
Now, so we developed a model more to do with seeing how we could integrate our noise into that model to see if it would improve. We're still working on that solution. So that's an ongoing one. So we're kind of trying to adapt and trying to get inspiration from existing public, open source models, and then add our layer of expertise to that. So we're not really trying to invent a new one just yet.
Okay.
Now, that's not to say we have ambitions to do that, particularly when it comes to using the quantum core itself. So the quantum core has some nice characteristics in that it acts. Um, it's a very good piece of physics hardware to find a minimum in an energy space, and that's what we want to use that to accelerate the training. But there's a lot of steps along the way to map the energy in your network to the quantum computer and then extract the data back. So lots of bits in the middle. I can see um, lots of areas to be developed, and that's what we're doing right now. We're thinking about that, but that's quite a bit down the road.
Okay, so you just told us that you were using mask RCNN and RCNN for COVID using
Mm.
X-ray. So would you mind elaborating on that a little? Because that's sort of interesting for us at the moment.
Yeah, so that was quite an interesting project we did during the summer to take um, I guess, the kernel for the mask or CNN,
Mhm.
take public domain or public data sets and see, okay, let's just first of all see if we can achieve, within the top 50 scoreboard on Kaggle by just tuning this with hyperparameters and running this ourselves using nothing more than a Google Colab notebook.
Mhm.
So no, nothing, not a lot of sophistication, but just bringing in our own knowledge to bear here. So once we did that, we wanted to then take it apart and seeing, okay, now how can I improve this training set so that it can take advantage of, so we can use things like noise or unitary noise that you get from a quantum computer. And that's kind of the work that's ongoing right now. We're still looking at that. We're kind of coming back to that. We need to do that at a larger scale because we need to sweep a number of hyperparameters, and all this takes time. We don't want to use transfer learning. So initially we did use transfer learning because we want to actually show that we're learning faster. Um, so we're kind of taking apart a lot of the techniques that would normally be used for mask RCNN, putting it back together. But this time we're adding what we believe is the product, the noise that we're generating from a quantum computer into that.
So did you make it into the top 50 on Kaggle?
So we made it into the top 90.
Okay, well, that's sort of a good start, I guess.
That's a well, I'm pretty happy with that, given we only spent maybe 3-4 weeks on it. Two people with simply just using a collab. We didn't have any, we didn't have a lot of CPU power. I think today we could do a lot better because we acquired a bunch of servers with some nice GPUs on them. So
Mhm.
I think we could explore that space a lot more.
Okay, cool. So this is my last question. What would be the number one skill or competency that you think a PhD graduate should have in machine learning?
The number one, I think it's you really need to understand what every line of code is doing. I couldn't emphasize that more.
Mhm.
We're using tools PyTorch, we're using KRS and PyTorch, but quite often, unless you really understand well what actually is going on underneath the hood here, it's going to be very difficult to make solid progress and to understand what's going on. Machine learning models themselves are very, very difficult to explain why they perform well or why they do not perform well. So until you kind of dissect the problem, understand, okay, what's going on in this, this matrix multiplier, what is it actually doing? I think that fundamental understanding is really important. Having a really good, solid understanding of, okay, what's really underneath this model when I ask it to do the following operation, what's going on. That's for me. That probably helps because I come from a hardware background, so I don't. I kind of need to have an intuition about what's the hardware looking like underneath all this. What's it actually doing? And so I think that helps a lot.
Okay, so
Fundamentally, no.
just to clarify a little, since you also have mathematics background, so are you stressing over the mathematics behind all that as well? Or how would you describe?
But I think my expectation would be after doing a PhD, the mathematics would be second nature. You'd be very fluent in the mathematics because you kind of constantly come up against it. It's also knowing how you translate the mathematics down to, okay, if I had to write all this from, Python or even lower level, would you be able to do that? And that's the fundamental question. If you can do that, that's great because then you know what's going on. You know what these, what a keras layer is doing, what an nn.conv is actually doing. I know it sounds simple, but it's the simple stuff that allows us to make the abstractions to go to a higher level.
Okay, yeah, that is justified. Thank you so much. And anything else? Do you have any questions for me or something like that?
What areas are you interested
Okay,
in your
so
PhD?
I'm actually working closely with IoT devices. So right now I'm looking on serverless machine learning and federated machine learning to come up with some more general algorithm for IoT devices. So if
Hmm.
we have to deploy some machine learning model on different IoT devices, we could just have one general. We could that could just adapt to the IoT device and we don't have to be specific about it. Like don't train it over and over for each and every IoT device. That's what I'm working
And
on.
have you kind of limited what you think an IoT device in terms of its resources? Do you have an idea of what resources they have typically?
So the idea is IoT devices usually have very limited resources. Um,
Hmm.
I'm not entirely sure at the moment if I'll be working with the imagery data or what. We're still sort of like narrowing down, but that would be like I think the most challenging part would be limited resources. That how am I going to deploy the machine learning model in the environment?
Yeah. Okay. So, I mean, I've worked in the IoT space for about 4 or 5 years, and we did two types of projects. In most cases, the number one thing for the IoT guys is battery power. So they do not want to change the battery of a deployed IoT device, typically because they're installed in difficult to reach locations.
Mhm.
You only want to replace the battery once every 5 to 10 years. So that's your number one constraint. You'll find that, okay, send data down like weights is expensive
Yeah.
because they have to receive, you have to turn the device on, it has to receive, it has to do reconfiguration, calibration, send it all back. So that's a huge limitation. Typically, IoT devices are switched off for long periods of time, which is actually quite a nuisance. And you might find that's that inhibits what they can and cannot do, even to upgrade their ability to, for federated learning. So that's they kind of almost go counterintuitive to what you want them to do. You kind of want everything to be in sync to a certain extent, but they don't want to be in sync because that's going to consume power. So you're battling against the power guys all the time. So your
So
major concern is battery
what
life.
general idea I have right now is to train a central model, and then we'll use serverless to invoke that
Hmm.
model. And whenever the device is on, we could just use the data using federated learning on and
Mm-hmm.
train it locally. So like we will have a very small copy of the central model on each IoT device,
Hmm.
consuming the very low of its resources, but then we will use the local data to train and fine tune the model right there,
Yeah. Yeah.
which is the idea. Let's see how it goes.
Let's see how it goes. Yeah.
Yeah.
Good luck with that.
Thank you.
That's a very interesting project. Lots of applications.
Yeah. Thank you so much for your time. It was really nice talking to you. And
Okay.
I look
I
forward
hope
to
that's
talking
helped.
to you again soon.
Yeah, absolutely. Yeah.
Yeah.
Okay. Bye bye now.
Bye.